Okay, it is fine. Okay, it is good. Okay. Before spring break, we studied the process synchronization. You know that we have already studied the process synchronization, and we know I gave you one overview regarding the shared memory and its problems, and what is the critical and non-critical sections. Okay, and then finally, uh, to make the consistency in your code, we can do for some synchronization mechanism, apply some synchronization mechanisms to do to make our system or process consistent. In case if a process, if two or more process needs to access the shared memory. Okay, so how do we evaluate the synchronization mechanism? There are three things. One is the mutual exclusions. It means that at a given point of time, when a process executing a critical sections, other process cannot enter the critical section until executing process comes out from the CS or critical section. Okay, actually, two process cannot enter at a time inside a critical section. This is the first conditions. Okay, first properties. It must be satisfied. If two process enter the critical section at the same time, then there will be some inconsistency. It shouldn't actually do this. Okay. Well, and next condition is synchronization mechanism should be actually granted the progress. What is the progress? Actually, a way of making sure that if a process is not inside the critical section, then it will not block other processes from entering the critical section indefinitely. Actually, it means that a process is not inside the critical section, so this process actually shouldn't block another process for entering the critical section for indefinite time. Okay. And another property is bounded waiting. Bounded waiting is the way of making sure that exists a bound or limit on the number of times other process are allowed to enter the critical section after the process had made the request to enter the critical sections. Actually, it's a very long sentence. Actually, in summary, is that if a process actually shows the interest to enter the critical sections, actually this process shouldn't block for a long time. Okay, shouldn't stop for a long time for entering the critical section. Once a process actually interest to for entering the critical section, so this process shouldn't starve or block for a long time. Okay, so there should be some limits or limits of times, number of times, or limits of times a process actually should wait to enter the critical section. It shouldn't be wait for a indefinite number of time, kind of like this. Okay, so this if a synchronization mechanism satisfy these three properties, means that this is a good synchronization mechanism. Okay, so today we will start the some algorithm for synchronization mechanism. First one is the lock variable. Okay, by using the lock variable, let's see how can we implement a synchronization algorithms or mechanisms. Okay, okay. Let me check one thing that last time we. I also next week maybe we have first midterm. Okay, first midterm. Yeah, sorry, second midterm. Okay. Okay. So I'll talk you. I'll also announce again. I'll give you announcement. How many? Hopefully, it will be also 30 questions. And this time, I hope that I'll give 45 minutes because there is only one module. Okay. So total 30 question, and you will get 45 minutes. Means that one question you will get 1.5 minutes. Okay. I think that should be fine. because some question will be true and false. Okay, so it should be fine for answering the all questions. Okay, so first we let's check this. We will start our first synchronization mechanism. It is called the lock variable. Okay, before we start, let me share my screen on this whiteboard. Okay, I think you are able to see my screen now. Yeah. Okay, let me turn on my record video. It will be, then it will be clear now. Smooth. Okay. Okay, so first algorithm for synchronization mechanism, we'll learn the lock. We'll learn the first algorithm name is lock variable. Okay, lock variables. Okay, the lock variable actually it's lock variable. It's work as like a like a uh, like a global variable of a function. Actually, two process can access this kind of variables. Okay, these special types of variables is available in operating systems. So this is or your or your programs or your programs as well. Okay, in your program, so you can use this lock variable to manipulate the synchronization mechanism. Okay, lock variables. Also, we'll learn the semaphore as well. Semaphore, another synchronization primitive. We'll learn this thing later. Notice today we learn this lock variables mechanisms. Okay, you know that it is now synchronization mechanism is that two process cannot inside at a time in a critical section. Also same thing is for if you if you consider the thread. Okay, two thread cannot also uh, cannot enter inside the critical section at the same time. Okay, this same thing for the process apply for this process as well as the thread as well. Okay, so now let's check this how lock variables mechanism works. Okay, so you know that in your critical section, you already know about this. This is the programs. Let's say this is the critical section for a process. Here should be some non-critical section of code, and here is some also some non-critical of some code. Also, between this code, there is kind of entry section. There is a small piece of code you need to write for entry section. We call it entry section as well as the exit section. This is the exit section. Okay, these two sections you need to write to maintain the critical section. Okay, critical section means that in this section your process will access the shared memory or shared variable. Also in this critical section, two process cannot be entering the critical section at the same time. Okay, now let's see how you write this entry section by using these log variables. Okay, log variables. Okay, so how log variables work? There is two lines for entry section. First line is while. Okay, at first I need to mention that at first initially log value is 0, and then initially log variable is set to the 0, always 0, and then two lines code is while for this. I am writing the code for this entry section for means that to enter the critical section, these two lines needs to be satisfied. While log not equal 0, not equal 0, 0, then okay, let me erase in here. You can be, this is for empty section code I'm writing in here. This is critical section. This is, let's say this is for non-critical section. Here you need to in entry level code is like this, while lock not equal 0, then it is just looping through this while loop. Here is semicolon means that it will actually loop through this while loop always, nothing to do in here, and then it will make this lock 1. Then next line it will make this lock equal 1, and then entering the critical section. What is the exit section code? After exiting this code, it just reset this log variable. Log equal, make it the 0. Okay. But initially log value is 0. Initially log value is 0. Log is not equal 0 means that log is 1. Okay. If log is 1, then it will actually loop through this while loop. Okay. Now this log variables. Also log is kind of boolean type variable. It takes only 0, either 0 or 1. Two values can take. Okay, it can take. Okay, but initially log value is 0. Now let's check for process. Every process we have some critical section, NCS, and also non-critical section, also critical section. And here you need to write this NT level code if you use this log mechanism, also exit level code, and then for and some another codes. Okay, this is, let's say this is for process P1. If it is process P2, also process P2, you may have this non-critical section and then critical section, and between this critical and non-critical code you need to add this first is this 2 line for NT section and this 1 line for non exit section, and then some others code. Also for process P2 is also the same thing. You know that this is kind of, if it is this is the CS or critical section, then you need to add this 2 lines of code to enter in the critical section, and after exit you need to write this. After exiting this critical section, you need to add this log is 0. Okay, this is same code. So so I can give this example by this way, that this process also it is same thing. I can use this process P1 by and give the and I'll explain this. This is the code segment for process P1, also P2. This is the code segment for process P2, but it is different code segment. Okay, different code segment. Don't confuse that it is the same code segment for process P1, P2, but it is same format. That's why, for understanding purpose, I will give this. I will actually explain from this code block. Okay, now let's check this how it works. Okay, let's see the process P1 first. There is two process. Let's consider two process first. Process P1 and P2. Okay, P1 is now executing its code, so it executes the non-critical section first. Then what it will do? Initially, I just tell you this lock is 0. So while lock not equal 0, then it will actually loop through this while loop, but it is lock equals 0, so it is fine. So it will make this lock now 1. Lock will be the 1, and then it will enter the critical section. Now process P1 is entering the critical sections, and then when it is come back again, it will make this lock value is 0. Lock value is 0, and then executing this code, and then it completes its executions. Okay, let's check this process P2 now trying to execute. This lock is not equal 0. Okay, not equal 0. It is fine. And then it will make this lock equal 1, and then it will P2 also enter in the critical section and make its lock 0 and complete this code. Now check some others conditions. Let's see at first lock is 0, log value is 0, initially log value is 0. Process P1 trying to enter in the process P1 executing its code is process P1 is scheduled by the operating system, and it's trying to executing its code. So it's execute the critical non-critical sections, as well as the lock is 0. So it will make this lock now 1, and then process P1 entering enter the critical section. Okay, then process P2 is trying to enter the critical sections, execute. Then process P2 actually is scheduled by the operating system. Then P2, what P2 will do? P2 will execute its non-critical sections, and here process P2 while lock not equal 0. Here lock is 0, or lock is now 1, because P1 is now currently entering the critical section. One process is currently enter the critical section. So you see here this lock is 1. So P2, when trying to enter in this critical section, it will be the loop through in here, because already one process inside this critical section. So it will execute this while loop again and again, because log value is now 1. P1 make this log value 1. So P1 is currently executing the critical section. So P2 is always looping through this while loop until P1 exits the critical section. Here P1, let's say after certain times, P1 also again is scheduled by the operating system, and P1 completes its critical section and make this log value 0. And then again P2 make trying to P2 actually scheduled by the operating system, and here it was printed last time in while loop, so it will start from this place, and now it will see this log value becomes 0. It is not equal 0, condition is false, and make this log value again 1, and P2 will be enter the critical section. Okay, this is the mechanism, and P2 also now again P2 is now currently entering the critical section, lock is 1. Now P1 is trying to enter the and get the scheduled by the CPU, scheduled by the operating system, and then P1 execute critical section. Here lock is 1 because P2 is already entered the critical section. So P1, what will do? P1 actually loop through this while loop until P2 finish completes this critical section and make the log value 0. Okay, this is the mechanism for actually basic mechanism for this log variables. Okay, log variables, 2 lines of codes, and one process inside this critical section lock is 1. So another process, if another process trying to enter in this critical section, it will loop through this while loop. Okay, it will just busy with this while loop. Okay, it will execute only the while loop. Okay, while loop. Okay, it actually doesn't do any significant things, just execute the while loop until another process completes its execution for critical section and makes the log value 0. Okay, fine. Okay, do you have any questions regarding the log variables? So this is the first algorithms we're currently talking about. Okay, let's move forward, and then let's see what is the next. Okay, now this is a log variable. Now you know that there are 3 properties. We already mentioned that it is to evaluate a synchronization mechanism, whether it is good or bad. Okay, there is 3 properties. First one is mutual exclusion. Okay, mutual exclusion. Okay, mutual exclusion means that 2 process cannot be critical section at the same time. Okay, 2 process cannot be enter the critical section at the same time. If it is 2 process enter the critical section at the same time, then actually there will be inconsistency. Okay, so what is the let's check this, whether this lock variable mechanism, synchronization mechanisms, satisfy the mutual exclusion or not. Okay, guaranteed the mutual exclusion or not. Okay, let's check that one. Look at carefully. So here you see that let's check process P1 first time. Process P1 is trying to enter. Process P1 is scheduled by the operating system. It's execute its non-critical section. Then at the beginning, at the initially, log value is 0, always 0. Log variable is 0. It is kind of global variable, so you can consider it. Is 2 process, every process, not 2 process, any number of process can access this log variables. Okay. So log value is 0. So it is log is not equal 0. So condition is false. So it will make this log equal 1. Okay, log equal 1. Okay, log equal 1. This line. Okay, log equal 1. Second line for this line. Okay, log equal 1. Okay, after making this log 1, let's say P1 process P1 is printed. Process P1 is printed. P1 is stopped by this by operating system or CPU. Stop this process execution the process P1. P1 gets printed by the CPU, and P2 is scheduled. Okay, now what's happened here? Oh no. Let me explain this. Okay, let me explain. Log is 0 at first, and then what's happened? Log is you see this here, the log value is at first let me actually redefine it. I made one mistake in here. Let me re-explain that thing. At first P1 will execute the non-critical sections, and then it will execute the while loop, and then while log not equal 0, Not equal 0 means this condition is false. Lock is 0 now, currently 0 now. So condition is false. So in between while loop, then this process P1 is preempted by the CPU. Lock is still 0. Lock is still 0 means that in this line, after executing this while loop, between this lock, in here process P1 get preempted. It actually P1 doesn't get enough time to convert this log value as 1. Okay, log value is 1. Okay, here between while loop, while and log variable, between these two line here, after executing this while loop, P1 get preempted by the CPU. Next, process P2 will be scheduled. Let's say process P2 is scheduled by the operating system. Here P2 will schedule the executes the non-critical section. Then what P will see in here? P will see that P2 will see that while lock not equal 0. Yes, lock not equal 0. Lock is 0. So it execute this line and it will make this log value as a 1. P2 is make this log value as 1. So P2 is now currently enter the critical section. Okay, P2 now currently enter the critical section. Okay, now let's say again P2 got printed and P1 again is scheduled by the operating system. Also, you know that after scheduling the any process, start execution when it gets printed. Okay, it never execute from the beginning, so it will get P1 last time P1 printed from this after this while loop. Okay, after this while loop in this here actually process P1 was printed. So process P1 will be in here. It will process P1 currently will not check this while loop because P1 last time process P1 was printed after the while loop. So again process P1 will be make this log value as 1, and enter the critical section P1. So now you see that P1 and P2 both are entering the critical section at the same time. Okay, it is possible if a if a process is printed after the while loop, after this while loop, then there is a chance uh, chance for entering the two or more process inside the critical section at the same time. Okay, at the same time. So from here you can see that this log variable mechanism it doesn't guarantee the or satisfy the mutual exclusion. Okay, this is the one of the, this is the major properties for actually synchronization mechanism. Okay, so log variable doesn't satisfy the mutual exclusion because two or more process can enter the critical section at the same time. Okay, so mutual exclusion doesn't grant it, is not granted by these log variables. Mutual exclusion is not granted by this logs variable. Let's check another is progress. Progress is satisfied or not. Okay, progress. Okay, what is the progress? Progress is nothing but when a process is not enter the critical section, when a process is not in a critical section, so it doesn't actually block this another process for entering the critical section indefinite time. Okay, indefinite time. Okay, now let's see that this mechanism satisfy the progress or not. Okay, let's say process P1 is trying to enter in the critical section. At first P1 is 0, so and make it the log value is 1, and it will enter in the critical section. Okay, it will enter in the critical sections. And let's say process P2 is now trying to enter in the get this schedule, and it cannot actually process P2 cannot enter the critical section because P1 is already inside the critical section. Once the P1 outside completes the critical section and make this log value 0, then process P2 get the schedule and then it can enter the critical section. Okay, but process P2 can actually execute the non-critical section codes. Okay, even though process P1 inside the critical section. Okay, so progress is satisfied by this kind of techniques. But one thing is that let's say the process P1 is scheduled by the operating system and it will make this log value is 1, and in this code before entering the critical section P1 get printed. printed by the operating CPU. Next, P2 is trying to execute the code. It executes the in this position. Also, it will get this lock is one. Lock is one because lock one, and then but process P1 is not inside the critical section. Okay, but it is still block this process P2 for entering the critical section because P1 is printed in this point. Okay, before the after making this lock one and it gets the printed in here. Okay, so in this case also it doesn't guarantee the progress as well, but it is not indefinitely. Once the P1 actually gets the schedule by the CPU by the operating system, and then it will actually execute the CS or execute entering the critical section because next line is for this critical section. Okay, so it is said that the progress is satisfied by these log variables. Okay, but in some region it may not satisfy because you know that after this log value before this critical section, if a process got printed, no process is now currently entering the not in a critical section, but process P2 is trying to enter this critical section. Here it will find this log value is one because after log making this log one, P1 got the printed. Okay, this is how it can be little bit make some it can actually do it can actually hamper this progress for this process P2, but it is not indefinite. Once the process P2 get the CPU, then next line is the critical section. Okay, next is critical section. Okay, that is the reason sometimes it's called this. It is known as this. It satisfies the progress. It satisfies the progress. Guarantee the progress. Okay, log variable guarantee the progress. But let's check this. Another is bounded waiting. Okay, bounded waiting. Okay, let's check this bounded waiting satisfy or not. To actually ensure this boundary waiting, let's check another let's use another infinite while loop in our code segment. Then we can say that log variable satisfy this bounded waiting or not. Okay, here is not equal 0. Okay, let me write it again, this two line of code. While log not equal 0, then it will be in here, and next line it will make this log equal 1. Okay, now let's check this whether bounded condition is satisfied or not. That's our code segment is enter both process code segment is inside a infinite while loop. Now let's check that whether bounded condition is satisfied or not. What is the bounded waiting? Bounded waiting means that here is we consider these two process P1 and P2. Once this P1 completes its critical section, and by this time P2 also enters to enter this critical sections. Let's check this. P1 actually can starve or can stop this process P2 indefinite number of time for entering the critical section or not. Okay, if it is if P2 actually P2 can block this block if P1 block the process P2 if P1 block the process P2 as indefinite number of time, that time we can say that bounded condition is not satisfied. Okay, now let's check this process P1 inside a while loop, and then it will at first log value is 0. So what it will do, it will do check this log is not equal 0, so it will make this log as 1, and then it will process P1 is entering the critical section. Okay, critical section, and P1 get printed, and P2 is scheduled by the operating system, and operating system and P2 executes its non-critical section, and here it will check this log is 1, so it will execute this while loop. Okay, this while loop again and again. Okay, again and again, then after that, after some point of time, P1 again get the CPU, and then completes its execution, and make this log value 0, and and execute the non-critical section, and then again it back to the while loop, and then again it's P1. Now we consider this P1. P1 execute the non-critical sections, and here it will see that okay, when it becomes zero in here, when it's actually exit log value becomes zero in here. Okay, so log is turned into zero in here. So P1 again back in here, and then while log not equal zero, here is condition is fine, zero, log is zero, not one, and then again it will make this log one, and then again P1 can enter in the critical section. But again, let's say again P2 is scheduled by the CPU. P2 will find this lock is 1. Again, P2 will execute this while loop only. Okay, it's back. And then P1 again, let's say back compilates the critical section and make this log 0, make this log 0 again. And then again back to the while loop, and then execute non-critical section, and also while loop, here it will check this lock is not equal 0, condition is satisfied, lock is 0 currently, and make this lock 1, and again P1 can enter the critical section. Okay, and let's say and by this time again P2 is set, P2 is scheduled by the CPU. Still P2 will execute this while loop. Okay, it will see that P1 is still in critical section. Okay, but P1 is executes this critical section again and again, can execute again and again, make the process P2 start or block. Okay, so bounded waiting is not satisfied by the log variables. Okay, because one process um, can actually execute these critical sections again and again, even though another process actually shows the interest for entering the critical section. These processes can be blocked. Okay, can be blocked. Okay, so bounded waiting doesn't satisfy in this synchronization mechanism. Okay, any questions so far? Okay, so our next algorithm is TSL algorithms. So before we start the TSL algorithms, let's check this why actually log variables doesn't satisfy the bounded conditions. Sorry, mutual exclusion. Okay, this is the major properties for a synchronization mechanism. Okay, for any synchronization mechanisms or algorithms, you can say this is the major property. If any synchronization mechanism break the mutual exclusions, it actually doesn't give any doesn't actually refer any it actually doesn't guarantee anything uh, for actually inconsistent result. Okay, this is the main or major properties. Okay, synchronization mechanism should satisfy the mutual exclusion. Okay, now let's check this why before we start the next algorithm called the TSL. Okay, so before we start the TSL, let's check another some properties for this lock mechanism. Okay, I missed this property. Some properties for lock mechanisms. We know that it satisfies only the progress, but sometimes it may miss the progress as well. Also doesn't satisfy the mutual exclusion or bounded waiting. Okay, some properties is for lock mechanism. It is multi-process solution. Okay, any number of process can use this mechanism. Okay, use this mechanism, any number P1 P2 till n number. Okay, any number process can use this kind of mechanism. Why it is multi-process solutions? Uh, in later we will see some algorithms that can actually synchronize algorithm then that apply only two processes. Okay, but this type of algorithms you can apply for multi-process. Okay, any number of process. Okay, and then synchronization process, this is busy waiting. So busy waiting synchronization mechanism. Okay, busy waiting. There are two types of synchronization mechanism. We are currently learning the busy waiting solution, busy waiting solution, and another is non-busy waiting solution. Okay, two types of synchronization mechanism, non-busy waiting. Okay, two types of synchronization mechanisms. Currently, we are working on this. We will see this non-busy waiting solution later. No worries. So busy waiting solution. What does mean this busy waiting solutions? You see that here once a process shows interest for entering the critical section, it executes the but another process is already entered the critical section, it executes this while loop. Okay, while loop, this unnecessary, okay, unnecessary tasks. Okay, CPU is busy, it will execute only the always this while loop. Okay, this is for unnecessary. Okay, it doesn't actually, it is not a part of your part of your main programs. Okay, this is for entire exit section. So these things while loop also needs to, your CPU needs to execute again and again. Okay, once it's scheduled by the operating system. Okay, to CPU. So this is busy waiting solution. Another is non-busy waiting solution. We will see the later. In non-busy waiting solution, uh, you need to use some system call or kernel call to make this non-busy waiting solution. We'll see later. Notice also this synchronization mechanism implement in user mode. User mode means that in user process you can implement this synchronization mechanism, because here you don't require to need to call any system call. You just manage one log variables. Okay, in your code. Okay, in your code you need to maintain a log variables. So you don't require to call any kernel method. So it can implement in user mode. Okay, in non-busy solution, when you see that non-busy solution, you need to call some function from the system or kernel. So this is not you cannot implement actually in user mode. Okay, but this process you can implement in user mode. Also, no hardware support is required. Means that to implement this algorithm, you don't require any special hardware support, or any special hardware support means that some special commands, special actually command. Okay, in later algorithms you'll see it is there is some special command. So most of the hardware may not support this type of command. We'll see in later. Okay, so this process actually doesn't require any special hardware support. Okay, our next algorithm is test and set lock. Okay, test and set lock. Okay, test and set lock, or TSL mechanism. Okay, TSL mechanism. Uh, so before we start this TSL mechanism, let's see why actually mutual exclusion doesn't guarantee by the log variables. Okay, it is kind of some improvement of log variables mechanism. Okay, TSL, test and set log mechanism. Okay, it is just improve just updated format for of log variables. Okay, now let's see that how you can implement these log variables. Log variables, you know that log variables, I already showed you this log variables. You have two lines of code. First line is while lock not equal 0, just execute this while loop. And then next line you make this lock equal 1, and then enter the critical section. And next is just make this exit section, make the after complete the critical section, make this lock is 0 again. Okay, and then this is kind of, and non-critical section could be in here. Okay, now let's check this how you can implement these two lines of code by using this assembly language. Okay, assembly language, this two line of code by using this assembly language. How assembly language works: at first, to implement this code, you need to load the log variable, some register log variable, let's say register R1, and then you need to compare this register, compare this R1 with a number 0. If it is 0, if log value, if R1 whatever value is register log value, you just load it to the R1, and then you compare this R1 with the value 0. If it is 0, then what's happened? There is in computer there is one called this 0 flag. Okay, 0 flag. Okay, then 0 flag will be set. 0 flag will be 1 if it is 0. But if it is not 0, jump. If it is not 0, if 0 flag is not 0, then you jump to the step. If it is step 1, this is 2, this is 3 line, then it need to jump the step 1. Okay, if it is not 0, means that R1 is not a zero, log value is not a zero. Okay, this is how, then it will be this how a loop. This is equivalent to this line of code. Okay, this line of code, 3 lines of code is required in assembly, and then fourth line is log, make it this log 1. Okay, how we can do this? Store command. By using store command, you need to enter this number 0, sorry, number 1, sorry, number 1 to store number 1 to log. Okay, log, and then cs. This fourth line is equivalent to this assignment operators in high level. Okay, store log to 1. Okay, and then in exit section, what you need to do? Exit section is fifth line for exit section. Store number 0, make this make value log as a 0. Okay, so log will be the 0 after this after executing a theoretical section. Okay, why I make it for assembly code? Usually I just previously, you know that your CPU will execute code, executed line, every instruction by instruction, every instruction. And we can see that in high level code, instruction, high level code, we just mentioned it due to actually understanding purpose, we just mentioned it's line of code. Okay, it's line of code, but this single line of code actually creates this 1, 2, 3 instruction. Okay, actually your CPU executes these 3 lines of code to implement this while loop. Okay, this is 1 instruction, 2 instruction, 3 instruction. This is actually actual instruction. Okay, when you write in it assembly code. Okay, also CPU, your CPU or computer doesn't know this load and whatever it is assembly code, but CPU will, your computer will know this machine code. Okay, machine code is 0 and 1, 0 and 1. Machine code is nothing but to represent this line of code by using 0 and 1. Okay, 0 and 1, but same here is 1, 2, 3, 4, 4 instruction. Also machine code will write this corresponding 4 instructions, 0 and by using 0 and 0, 1, 0, 1 binary representation. Okay, so this is the actually instruction. When you compile your code, high level code, you compile, then it gives this assembly as well as assembly, and then machine code. Okay, machine code. Okay, machine code. So this is the machine code, and this is how actually a program will run by instruction. Okay, now let's check this. Why actually your lock mechanism doesn't satisfy the mutual exclusion. Okay, let's check first this first line. Your process P1, let's say we have two process P1 and process P2. Okay, P1 execute the first line of code, first instruction, and then got printed. What process P1 do? Process P1 make it as a log, just log value, whatever it is, log value. Log is at first, log is initially 0. Okay, process P1, what it does? P1 is store the log value to the register R1. Okay, to the register R1. In, if it is CPU in here, it will, what process will do? It will store this log value, load the log value in register 1, and then let's say in this line process P1 got printed, and P2 is let me write in here. Okay, P1 just execute the first line of code, execute its first line, first P1 execute the first line of code, and then got printed. Okay, then process P2 got the CPU, and it executes the P2 got the CPU, and what's it will do? It, let's say it execute all 4 lines, okay, or for all 4 lines of code. 1, 2, 3, 4 lines of code. How it's work? It will load the log to R0. Log is 0, so it just override this log value. It just override this register R1 value as a 0 when it gets the CPU process P2, and compare this R1 is not equal 0 compared to R1 is 0. Yes, R1 is 0. Jump, if not 0, then 0 flag will be set. Jump if not 0 will be the false, okay? Because R1 value is 0. So 0 flag will be the set. If it is not 0, then it will be jump. Okay, then store lock is a log value as 1. So log value is make it the 1 in here. And then P2 will be entering the critical section, okay? Now let's say again, P1 is scheduled by the CPU, again operating system, and it will, what it will do, it will start from again this line, okay? It was got printed from this one line. So number 2 line it will execute, okay? Number 2 line, it will get, it will, what it will do when it is restored, it will make this R1 again 0, and then it will compare this R1 is not equal 0, condition is equal 0. So 0 flag will be the set, 0 flag will be the 1. Jump, not 0 flag, okay? Not 0 flag is step 1, but 0 flag is 1. 0 flag is set, and make this store the lock is 1, store this lock is 1, just override this lock variables, and then enter in the critical section. So from here you can see that if P1 is printed after this, after the first line of execution, both process can enter in the critical section, okay? Okay, let's check again that process P1. Let's check another. First we can say this, after executing this number line number 1, P1 got printed, and it can also execute the critical section. Both processes can execute the critical section. Now check this, P1 printed after executing the second line, what's happened, okay? Okay, let's check P1 is start the, got the CPU, P1 completes, makes this, execute the line 1. So line 1 load the log value in here. Log value is initially 0. Log value is 0. So it will load this log value as register 1, register R1, and then compare this R1 to 0. Yes, R1 is 0. So 0 flag is set, means 0 will be the 0 flag will be the 1. And then P1 got printed after this, executing this line 2. Okay, line 2. It just said the 0 flag is set after line 2. Now P2 got the CPU, and P2 execute all 3, 2, 1, 2, 3, 4 line, and can enter the critical section. Let's check. Okay, log will be the log value will be stored in R1. It is 0, and then what it will do? It will compare this R and 0. So it is 0. So 0 flag will be the set. It is not 0, so it will not jump, and store the lock as a 1. Lock as a 1, and then P2 can enter the critical section. Okay, P2 can enter the critical section after executing this 4 line. Okay, let's see again. P1 got the CPU. CPU again. P1 last time execute 1 and 2 line. So now it will compare this third line. Okay, third line, not jump, not 0, step 1. Okay, if so 0 flag was set last time. So here it will not, it will be the false. So it will store the log again 1, just rewrite, and then P1 also can enter the critical section. Both process can enter the critical section after the second line of if P1 or a process after executing the second line. Okay, second instruction. Let's check another. If it is printed by the third instruction, what's happened? P1 execute 1, 2, and 3 lines, and then got printed. What's happened? Here, load the log R0 is nothing but 0 in here, and compare it. So it will be the true. 0 flag will be the set. So it is not 0. This will be the false. And then in here, P1 got printed. Okay, P1 got printed in here after executing the third line. Okay, now again P1 is P2 is scheduled by the operating system. So let's say P2 again, it will execute 1, 2, 3, and 4th line. Okay, let's check what's happened here. Load log to R1. Lock is 0, so it will be the 0, and compare this R1 register value with a 0. So it will be the equal 0. So 0 flag will be the set, and then jump not 0, step 1. If it is not 0, then step 1, but it is 0 flag set, so it never jump. So it will store the lock as a 1. Make this lock is a 1 in fourth line, and then P2 will be entered in the critical section. P2 can enter the critical section. Now let's say again P1 got the CPU, and it will execute, it will actually preempted after 3 lines. So it will store the log value fourth line. It will store the log value to 1. Log value just override this log value, and then also it can enter the critical section. So both P1 P2 can enter the critical section if the process P1 preempted after the third line. Okay, let's check this fourth line. What happened fourth line? This is the last check. P1 got the CPU and it's execute 1, 2, 3, and fourth line. First initially lock is 0. Okay, lock is 0. Then what's it will do? Load the lock to register R1. Register R1. Here is the register R1. This is register R1. And then compare to register R1 value with a 0. So it is 0. So 0 flag will be the set. It will not jump in here, and store the lock as a 1. Make this lock as a 1 in fourth line. And then in here, P1 got printed. Okay, P1 got printed and execute the process P2. What's happening here? If process P2 1, 2, 3, and third line, let's check this way. And what's happening here? And let's say after fourth line, P1 is entering the critical section. Okay. And now P2 got the CPU, and P2 will load the lock to R1. Now lock is 1. So here is 1. Because P1 already make this lock value 1 and enter in the critical section. Okay. So lock is 1, and it will compare this 0, compare R1 value with 0. So 0 flag will not be the set. So not 0, it will stop. It will just loop through in here. Okay. If loop through here, so it is loop through in here. Okay. So it cannot, P2 cannot enter the critical section. Okay. Because log value is currently 1. It made by the process P1. Okay. So from here, you can see that this process P1 or first process, any process, if it is preempted between after this load after this first line till third line, between this line, 2 process can enter in the critical section. If it is preempted after this store the log value as a 1, then only 1 process can enter the critical section. So what actually TSL does, TSL make this, actually it's rearrange this code, rearrange the code. What TSL does, it TSL actually observe that if anytime a process is preempted between load command as well as the store command, then actually there is a chance 2 process can enter the critical section. But if it is if a process preempted after the store the log value, then it never actually 2 process never be enter the critical section at the same time. Okay, if it is stored the same time. So what TSL does, TSL makes some rearrange some this assembly this code like this way. First line is, okay, let me on my, okay. First line is, what TSL does, first line is load lock to R1, and second line is compare, second line is store 1 to lock. Okay, 1 to lock. And third line is just compare CMP, compare this value R1 with a number 0, and then fourth one is jump if step 1 jump step 1. Yeah, this and then critical section. Okay, critical section. Okay, this it just make this, it just rearrange this, store critical section, store the log value after the load the register, after the log value register load to the register R1. Second line just second line you make this log value as 1. So from here you can see if a process is printed after executing the one line number 1, then there will be the chance for two process enter the critical section, because process actually it doesn't it's printed in here, but it doesn't convert or doesn't actually update the log value. Okay, log value. If it is only in this case, if the process is printed in this after executing these two lines, then it just updates this log value. So another process cannot enter the critical section at the same time. Okay, so here is here, and here three options, three times in three section actually, in 3 points. In 3 points, a process can actually can print it. Then two process can enter the critical section. Here only 1 point. 1 point. If it is printed in here, there is no problems. Only one process can enter the critical section. Only this point, if a process is printed in this point, then two processes can enter the critical section, because the process actually never because the process actually wouldn't get the enough time to store the or update the log value. Okay, only here only 1 point in here, only 1 point, but here is 3 point. Okay, so here actually it is better solution. But what TSL does, TSL make these two things as a single command. Okay, make it two things as a special command called TSL. Okay, make it TSL. Okay, load the log value to register and store the log as a log value to 1. Okay, it make it a single command. Okay, also you know that CPU your CPU will execute a process instruction by instruction. So TSL is a single instruction. What it does, it is equivalent to these two lines. Okay, these two lines. Okay, this is the tricks for the TSL. Okay, if it is single instruction, so when a process execute this first line, so it is a first line TSL, so it just load log value as well as store the log and also update the log value as well. Okay, so there is no chance to enter the two process at the same time. Okay, to the critical section. Okay, to the critical section. Okay, so from here you can see that this TSL can guarantee the mutual exclusion. Okay, mutual exclusion, because this is special command. It makes is special instruction and make this two instruction as a single instruction, as a single instruction. Okay, so mutual exclusion all will be satisfied. Now see the progress. Okay, progress also is grantee. So one process is come out of this critical section, it will make this log value 0, but once a process is not inside the critical section, means that log value is 0. So it's never actually it's never actually stop the process for entering the critical section. Okay, for entering the critical section if a process is not enter the critical section. Okay, so progress will be satisfied by these mechanisms. And let's check this whether bounded mechanism bounded waiting satisfy or not. Okay, for bounded waiting you need to use this infinite while loop in here. Okay, infinite while loop in here. Let's say process P1 first, it's go for this TSL, make the TSL is single line command. Okay, this is single line command. It is equivalent to store and update the TSL. Okay, TSL. So let's say process P1 first, and two process P1 and P2. First process P1 trying to enter the critical section. Okay, make this TSL means that load make the log value as 1, just simplicity, and then compare everything, and it will enter the critical section. Okay, enter the critical section. P1 entering the critical section. Next process P2 is trying to enter the critical section. So its interest, and it will be jump into jump in this step. Okay, this step, because lock is 1, make this lock is 1. Okay, lock 1, so it will be jump to the in here. Okay, it cannot enter the critical section. Okay, but process P2 shows its interest, but P1 is inside the critical section. Okay, P2 already shows its interest for entering the critical section. Okay. Now let's check this process P1 again can enter the critical section or not to stop the process P2. Okay. Okay. Then we can say this bounded waiting doesn't satisfy. If process P1 can again and again enter the critical section for waiting the process P2. Okay. Then bounded condition doesn't satisfy by this TSL mechanism. Okay. Let's check again. Let's see this process P1 completes this execution and it makes this log value 0. Log value 0. Again, it will back to the while loop and TSL make this log is a 1 and then completes everything, can enter the critical section, but and enter the critical section. And again, P2 is scheduled by the operating system. What's P2 will do? P2 will see this lock is 1. One process is already under the critical section. So it will just back through in here, look through in here. So from here, you can see that. And then again, let's say again, P1 completes this critical section, make this lock is 0. Again, it can back and make it everything and can enter the critical section, okay, by waiting the P2, okay. So one process can executes the critical section again and again by waiting the another process, okay, another process. So bounded waiting doesn't guarantee by this algorithms, okay. Bounded waiting doesn't guarantee, okay. It's guarantee the mutual exclusion progress, but bounded waiting, it doesn't guarantee by the TSLs, okay. So from here, you can see that TSL, some properties for TSL is also busy waiting solutions. Okay, busy waiting solution, I already mentioned that it's when actually a process, one process inside the critical section, another process is executes the unnecessary while loop. Okay, here is same thing, same thing. Once a process enter the critical section, it will execute the unnecessary while loop for making the CPU busy. Okay, okay, this is unnecessary. You just make this CPU busy. Okay, you just use the resource. Okay, that time another process can use the CPU, so it's degrade the performance of your whole systems. Okay, so TSL is also busy waiting solution. It is also multi-processing solutions. So any number of processes you can add this TSL mechanism. Also, you can implement these algorithms. One of the major disadvantages, it is hardware support necessary. Hardware support means that TSL is special command. Okay, TSL is special command. You know that load, CMP, and jump is not 0 is store. This is the command. Okay, but TSL is also kind of a special type of command, load, TSL. Okay, but this kind of load, CMP, it is actually available for every computers, okay, every hardware or computers, okay, every computers or CPU support this kind of instruction. But TSL command, it may not support this all hardware or all computers, okay, this command, okay. This is, you know, that this is a special type of command. It makes this two command, two instruction as a single instruction, okay. So TSL is a special command, so hardware support is necessary, okay, special type of commands, okay. So this is the one of the disadvantages for this TSL algorithms. Okay. Also, it is implemented in user mode. Okay. There, even though this is a special command, but here is you never call any system. You never call a function from a system or kernel. Okay. So you can implement these algorithms in a user's mode. Okay. Okay. Any comment or questions, Soba? Okay, if not, let's stop in here today. In our next class, we'll learn the strict alternation methods as well as some other algorithms called interested uh, 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 interested variables and other algorithms, and also we learn the Peterson method as well. Okay, these three algorithms hopefully we'll learn in the next class. If we have time, we will learn the more as well. Okay. So we can stop in here. So before we go, I just mentioned that in our next, we have, okay. Okay, next maybe your next Thursday, maybe 13 is your second mid exam. Okay. So module 4 will be only syllabus. Syllabus is for module 4 that you learn. Okay. It will be MCQ as well as true false type question, similar as previous. So total 30 question, you'll get the 45 minutes, okay, 1.5 minutes per question. Okay, this is small syllabus. So please read all PowerPoint slide, okay, carefully, okay. This is small syllabus, okay, plan carefully. Hopefully you'll get the better score, okay, if you read the each line of the slide, okay. Okay, any questions? Okay, if you do not have any questions, we can stop here and see you next class. Okay, have a great evening. Bye.